Alright, if you're watching this, that means that I did not get out of my meeting. So you're watching this. I was going to try to get out of it early. I'm going to try to get out of it tomorrow, so I can come to class, see you guys, but that probably won't happen. I'm just guessing. So I'm making this just in case. This also means you won't be having a quiz today, so you can relax about that. The homework, we'll check it Tuesday also. I mean, if you want to... Here. Alright, well, we'll just check it all on Tuesday. I'll give you the answers and everything. Today, I'm going to move on, give you some bunch of new stuff. Some stuff yesterday that we didn't get to because we were talking about maps. And then some new stuff and a nice big homework assignment for your 3-day weekend. That'll be lovely. So here we go. If you remember yesterday, we were talking about mean value theorem. I'm just going to start with like an example of how this was used in life. And if I explain it to you just without mean value theorem, it kind of seems like duh, but this is how it was used. My teacher from this summer explained this to me. He was talking about how he lives over on the East Coast somewhere, and they had a toll bridge. I don't know. Here's my bridge. Yeah, it's a nice bridge. Ooh, there we go. And when you pull up, there's like a thing, and you have to push the button, and it gives you a ticket. And then you drive across the bridge, and at the other end, you give the ticket to the dude, and then you pay your toll. I don't know why you don't just pay at one end or the other. Anyway, I don't know the whole story. Maybe there's different ways you can go once you're on the bridge or something. I don't know. But anyway, it went something like this, to where, let's say you pulled up. We're going to graph your progress over the bridge here. Here's your distance. Here's your time. And let's say you pull up, you get your ticket. That's your distance is 0, your time is 0. And you drive. And then we're going to drive a little faster, Okay. And then we get to the end of the bridge. And this won't be very realistic, but let's say it was 10 miles long. And let's say it took you 6 minutes. So 6 minutes would be 0.1 hours. Right, because 6 over 60 is 0.1. Anyway, he told the story of how this bridge was giving people speeding tickets. And, they didn't have them on radar or anything, but they could prove that they were speeding. Because, in this situation, if you went 10 miles in 0.1 hours, well, the slope of that line, right there, 10 over 0.1, would be 100 miles an hour. And they could prove then, using mean value theorem, at some point along your journey here, like we were doing yesterday, we must have a parallel tangent line. So at some point, you must have been traveling at least 100 miles an hour. It's kind of obvious when you think of it that way. It's like, well, yeah, if your average speed over an interval was 100 miles an hour, of course you must have driven that fast at some point. In fact, you were probably going over 100 miles an hour for most of it in order to average that, because you had to speed up and slow down. But, yeah, that's just one little example. I think you have a homework question that kind of deals with that, where you just kind of have to explain something like that. So there was some other little stuff we didn't get to yesterday, like this is all just kind of random little tidbits of stuff. Let's say we have a function, and this function is increasing. Remember, increasing means going upward from left to right. It's increasing on some interval what does that tell you about the derivative? So here's f of x. It's increasing on some interval. What can you tell me about the derivative of that on that interval? Or you can also think the other way. If you have a function that's decreasing on some interval, we'll call that one g of x. What can you tell me about the derivative on that interval? And it's got to be decreasing or increasing over the whole interval. It can't change. Like this one changes to increasing, but that's not in my interval. You can't think of this as, oh, like this. Oops, you can't see that. You can't have it change inside the interval. So this one, it's increasing over the whole interval. This one's decreasing over the whole interval. And if you have no idea what I'm talking about, all I was trying to get out of you was that, well, if the function's increasing over the whole interval, the derivative must be greater than 0. It must be positive, right? Because anywhere along that, the slope of the tangent line would be positive. Same thing over here. Slope of the tangent line would be negative always. So if you have a function that's decreasing over some interval, then the derivative of that portion must be less than 0. It must be negative. Seems kind of easy. Well, it is. But you can use this idea to know that if your derivative, if you know that your derivative, if you know it's positive or negative, then you know whether the function is increasing or decreasing over that same interval. I don't know why I started to write that. I should have just explained it. So yeah, if you have your derivative and you know the derivative is positive over some interval, then you can know that the function must have been increasing during that interval. If the derivative is negative over a certain interval, then you can assume that the function was decreasing over that interval. It's not really assuming, it's just knowing that that's how it works. So we can use that and do a couple examples here. Basically, I can just ask you, find the intervals where each of these functions is increasing and decreasing. Probably not going to have enough room, so I'm going to switch papers. So we'll do one. We'll go f of x equals x to the third minus 27x. And another one. G of x equals 3x squared plus 6x. I guess if you want time to try it, well, I guess you usually want to see one before you try it on your own. So I guess I'll just do number one for you. So all we got to do is, okay, where is this increasing and decreasing? Well, I know it's increasing where the derivative is positive, and I know it's decreasing where the derivative is negative. So I'm going to look at the derivative. So the first thing I need to do is find the derivative of this. Looks like derivative 3x squared minus 27. Now I need to go, okay, wherever this is positive, my function is increasing. Wherever this is negative, my function is decreasing. Well, so how do I figure that out? Pretty simple. Take that. Where it's positive means it's greater than 0, right? So solve for x now. Add 27. 3x squared is greater than 27 divided by 3. X squared is greater than 9. I don't remember if you remember how to do this, but it's not just, you can't just square root it and say x is greater than 3. I mean, that's one of the answers. It's like, when is this side bigger than 9? Well, if I square root both sides, when x is greater than 3, this is true, but also what happens? If x is negative 3, or, if negative 4, negative 5, if x is less than negative 3, then that's true, right? So we have two conditions here, and this is when my derivative was greater than 0, so this is where my function was increasing. So when x is greater than 3 or when x is less than negative 3. And then decreasing, we could do it again, but if it's not increasing, it's probably decreasing, right? I mean, unless it's a big flat part where the derivative is equal to 0. But on this one, I think you can imagine it's not that way. I mean, if I just took that and flipped it and did, okay, where is it decreasing? 3x squared minus 27 is less than 0. I mean, you can figure out pretty quickly that you get the same thing just with flipped signs. So this function is increasing. I like to write it like this. When x is less than 3, when x is less than 3, so it would be over here. Less than negative 3. But then between, I don't really know how I want to write this. Didn't really think that far ahead. I guess I could do, I don't want to do a number line. I can just write it like that. It's increasing there, so therefore it is decreasing when x is greater than negative 3 and less than 3. So between negative 3 and 3 it's decreasing. On the outsides of those it's increasing. Probably should have looked at how the book writes their answers. I don't know if I should put it on a number line or what. Yeah, whatever. We'll figure that out later. Minor detail. So if you want to try that one on your own first, pause it right now. If not, I'm just going to go ahead and do it. So hopefully, if you do, someone is walking to the computer now to pause it. Hopefully you've already done that. Now you're pushing play. Here we go. So this one, we'll just take the derivative. Let's see, 6x plus 6. Well, so where is it increasing? It's when it's greater than 0. And you can check increasing or decreasing first. It doesn't matter. 6x greater than negative 6 divided by 6. This one's a little easier. X is greater than negative 1 is where it's increasing. So when x is over negative 1, it's increasing. And if I do 6x plus 6 less than 0, I'll get the same. Oops, 6, negative 6. When x is less than negative 1, it's decreasing. And that makes sense because this is a parabola, right? So I kind of found my vertex. So when x is negative 1, this parabola, and I don't know, I shouldn't have even drawn my y-axis. I don't know where y-intercept or anything. I could figure it out, but I don't want to. I know when it's, so just ignore that. When x is negative 1, my parabola is decreasing. It's coming down. At negative 1, well, you notice there we have no equal to because it's not increasing or decreasing. There'd be a horizontal tangent. Slope is 0. And then when x is greater than negative 1, it's increasing. Horrible drawing. Hopefully you get the idea. So that's the whole increasing, decreasing thing. You'll see that in your homework pretty much exactly the same as what we just did there. Let's move on to some other 15 minutes so far for this video. Hopefully this uploads. Some other kind of random stuff that all goes along with this in some kind of way. If we have a constant function meaning no variable, like f of x equals any number, f of x equals 5. Well, you know the derivative of that, right? It's 0. Whenever you have the derivative of a constant, it's 0. And the reason, you know, if f of x equals 5, that's a flat line, so the tangent line has a slope of 0. Well, because of this, we could prove using the mean value theorem that if a derivative is equal to 0, then the original function must equal a constant. We can prove the converse of that. We're not going to prove it. If you want to prove it, you can go ahead and do that, but we'll just go, yeah, duh, of course that's true. We can use this because if we know two functions have the same derivative, so I'm just going to say two functions have the same derivative. Then they must only differ by a constant. I guess I should have said if two functions have the same derivative, then they must differ only by a constant. What I mean by that is, let's say our two functions, one is f of x equals 3x squared plus 2x plus 4, and one is 3x squared plus 2x minus 1. Both of these would have the same derivative. F prime of x would equal 6x plus 2. G prime of x would equal 6x plus 2. If I just gave you that and said, okay, here's two functions with the same derivative, and you're like, oh, well, they must be exactly the same except for that back number. You know, so that means that pretty much they're the exact same shape of graph and everything else. They're just kind of located in a different position on the xy axes. But we can use this idea, of course. Need new paper. And say, okay, if I know a function's derivative, so f prime of x equals 4x minus 3, and I know it goes through negative 1, 2, we're going to find, you can't see that, I put tape on here to kind of guide me so I don't have to stand up and look at the iPad. So if, right there, we're going to find f of x. So we know the derivative. We know a point that the function goes through. Now we're going to find the equation of that function. It's pretty easy. We just got to kind of go backwards and go, okay, if this is my function, or my derivative, then I can think backwards, and my function would be, how do I get 4x? I mean, what do I take the derivative of to get 4x? Yeah, well, that's easy. It's 2x squared. Derivative of 2x squared, I drop the 2, have 4x. And then this one was supposed to be minus 3x. Derivative of negative 3x, negative 3. But then, there could be some number out here. Probably is, just some random number chilling out there. Because when I take the derivative of that constant, I get 0. So it's not included. So we need to put that plus c out there. We're going to be using that a lot. Get used to that plus c thing. So my original function would be 2x squared minus 3x plus c. Well, now I need to figure out what c is. Luckily, I know my function goes through the point negative 1, 2. So I'll plug in negative 1 for x, 2 for y, solve for c, boom, done. So 2 equals 2, x is negative 1. c. Negative 1 squared is 1, times 2 is 2, plus 3 plus c equals 2. So that's 5. Subtract 5 from both sides. Looks like c is negative 3. So then, now I know my function must have been 2x squared minus 3x minus 3. Easy enough. You'll have to do that on your homework. This process of going backwards, of where I know the derivative and I'm going backwards to find the original function, that's called doing the antiderivative. Derivative, there we go. So, yeah, you'll see that word. It just means going backwards. So I'm starting with the derivative and I'm going backwards to get the original function that it came from. And we're going to do one more example of that right now, and then I'll give you your homework assignment. So, this is actually just one of the problems out of the book in this section. It's number 44. Oops, I don't think I'm on the screen. It's number 44 in section 5.2. It says, with what velocity will you hit the water if you dive off or step off a 10-meter diving platform? So basically, diving platform, water, it's 10 meters high. If you just step off of it, with what velocity are you going to hit the water? It may seem like there's not enough information, but there's plenty. Well, because we're assuming this is happening on Earth. So you should remember from physics that on Earth, the acceleration due to gravity is 9.81 meters per second squared, right? All right. Well, do you remember what we know about the relationship between acceleration, velocity, and position as far as derivatives are concerned? I know we did a little bit with that. I wish I was there right now to just talk to you guys about that, see what you remember. But I'm not, so I'll just tell you. If you remember when we did, like if we did position graphs, position versus time, the derivative of that, or the slope, that's your velocity, right? Because it'd be, position would be like meters per second. So the slope of that, meters per second, that's your velocity. So the derivative of position is velocity, derivative of the velocity, meters per second, that's your acceleration. So if I take the derivative of position, I get velocity. If I take the derivative of velocity, I get acceleration. Now we're going to go backwards. I know the acceleration. I want to find the velocity. It's kind of a long process, though. It's not as cut and dry as it sounds. So if I want to go backwards here, I know my acceleration. That's all I know, 9.81 meters per second. Well, if I want to go backwards, what would velocity be? Well, if I take the derivative of velocity, I get acceleration, right? So I just do my antiderivative here. So I know it would be 9.81. And in this case, t, since we're talking about time, you can put an x if you want, doesn't matter, plus c. You always got to add that plus c, that constant, because it could be there. So my velocity then, 9.81 t plus c, I need to solve for c.